Hi everyone, so here we are on Chapter 6, and Chapter 6 is on thermochemistry. As you can see right here are a bunch of terms that you can read on your own. Some of the ones that I will just review with you. So remember kinetic energy. Remember kinetic energy is the energy of motion. Potential energy is the stored energy, so it has the potential to do work later. And then some other terms when we talk about the universe. So when we talk about the universe is talking about what's happening between the system and the surroundings together. And we classify that as the whole universe. And when we say system, the system is basically where the reaction is occurring. Okay, what we are focusing on. Okay, that is the system. And then when we talk about the surroundings, everything else in the universe. So in other words, system is where the reaction is taking place, and then the surroundings are on the outside of that. And then you have your terms endo and exothermic, so you can review those right there. Exothermic, remember, that is where the heat is being released. Okay, heat is flowing out of the system, energy is being released. Endothermic is the opposite. That's where the energy is flowing into the system, and we say that the energy is being absorbed. All right, so those are just some terms that you should already be familiar with. And then let's take a look here. Okay, endo and exothermic. Remember, we can look at the delta H values, and the delta H values will tell us whether or not heat is being released or if heat is being absorbed. So if it's endothermic, all right, if it's endothermic, your delta H value is going to be greater than 0. So that means that that value is going to be positive, okay, if it's endothermic, all right, the heat is being absorbed. Therefore, if it's exothermic, that delta H value is going to be negative, all right? The negative sign is just indicating that the heat is being released. All right, so now let's take a look at this question here. Okay, go ahead and read it to yourself. And if you take a look at the reaction, we have solid sodium hydroxide, and then it's becoming aqueous. So in other words, we are dissolving it in water. All right, so when we dissolve the sodium hydroxide in water, it is going to release, so let's highlight this value, negative 43 kilojoules per mole. Okay, now it wants us to answer all of these other questions here regarding the dissolving of sodium hydroxide. So we are going to start off with 14 grams of sodium hydroxide. Okay, then it's asking us the first question, does the beaker get warmer or colder? So in other words, is it endothermic or exothermic? Okay, so let's just write down, right here. So if it gets warmer, that means you're going to feel the heat being released into the surroundings. Then that means it's going to be exothermic. If the beaker gets colder, I like to think about it in terms of it's taking heat away from the surroundings. All right, that's why it's getting colder. And then we call this an endothermic reaction. All right, so just by feeling the beaker, whether the heat is being absorbed or released, you'll be able to feel it. Okay, so just think about heat being released. You're going to feel that heat being released, therefore it gets warmer, and then therefore endothermic is going to be the opposite. All right, so just by looking here at this delta H value, this delta H value is referred to as the heat of dissolution. Okay, the heat of dissolution, meaning it is the amount of heat required when, or the amount of heat when the reaction is dissolving in water. Okay, and this is for the sodium hydroxide. So notice that it's going to release negative 43 kilojoules per mole. I said release because it has a negative value. So if it was, so this is telling us it's exothermic. Okay, see the negative delta H value? So it's exothermic. So that will answer part B. Is the reaction exo or endothermic? Okay, so we know it is exothermic, and you should make a notation because it has a negative delta H value. That's telling us the heat is being released. So if it's exothermic, the heat is being released, therefore the beaker is getting warmer. Okay, it is getting warmer. Now let's answer the last question. What is the enthalpy change for the dissolution? Dissolution, once again, referring to it being dissolved in water. So enthalpy change, okay, that is delta H. Delta H is enthalpy, and that is what we call the change in heat. Okay, so then all we're going to do is this right here, this delta H value, this is like our conversion factor. Okay, this is our conversion factor. It's going to release 43 kilojoules for every mole of sodium hydroxide. So start off with the number that's given to us, 14 grams. All right, so 14 grams sodium hydroxide we have to convert the grams into moles because notice in this conversion factor that we're going to use, it has moles in it. So we need to then therefore find the molar mass of NaOH, look it up on your periodic table, add up 1 sodium, 1 oxygen, 1 hydrogen. So if you do that, it should come out to be 40 grams per mole. Now we can use this conversion factor. So we're going to set it up so the units cancel. So these, pen option. So these grams will cancel. Now we are left with the moles on top. So that means we want the mole on the bottom so that those units will cancel out. So then the mole goes on the bottom, and then therefore the negative 43 kilojoules will go on top. Okay, so then those moles will cancel. Then that will give us our answer in kilojoules. So then we put this into our calculator. So 14 divide by 40, because that number's on the bottom, and then since this number's on top, that means we multiply. So then times negative 43, and then you get negative 15 kilojoules. Okay, so when we dissolve 14 grams of sodium hydroxide, it will release 15 kilojoules. Okay, so that is how you do that problem. All right, so now let's take a look at the next problem. All right, so now we're getting into calorimetry. So calorimetry is something that we did last year. Remember the MCAT equation? So the MCAT equation, delta H equals MCAT. All right, notice down here, I have that equation written here, but it's in a different format. So on your pink sheet, it might be written, I believe it does have it written with an S instead of a C. They represent the same thing. So instead of delta H, you might also see Q there, okay? Both of them represent heat. M is the mass, either the S or the capital C would represent the specific heat capacity for that substance. And then of course, delta T, change in temperature, is final minus initial. All right, so once again, always pay attention to the units. All right, always pay attention to the units. So let's go ahead and take a look at this sample problem. If 596 joules of heat are added to 29.6 grams of water, 22.9 degrees Celsius in a coffee cup calorimeter, what will be the final temperature of the water? All right, so we're going to use our MCAT equation. Now, if we take a look at all the information that we have the delta H, that is the delta H, that is the heat. We have the grams, and we have the initial temperature. Now, the one other piece of information that you will need is the specific heat capacity for water. So I will just tell you what that value is. The specific heat capacity for water is 4.18, 4.18 joules per gram degrees Celsius. That's a C there. Okay. All right. So then we're going to plug that value in for the C value. All right. So let's plug in the numbers that we have. All right. So delta H is 596 joules. The mass is 29.6 grams. The C value of water is the 4.18. And then the change in temperature, remember, is final minus initial. So we don't know what the final temperature is. So I'm going to put TF, final minus, and the initial is 22.9 degrees Celsius. All right, so now what we're going to do is solve for the final temperature. This is our missing variable that we're trying to solve for. So you need to do your math very carefully and solve for TF. Okay? So you should work this out. If you want to rearrange it a little bit, so then what I'm going to do is I'm going to divide by 29.6 and the 4.18 on both sides. Okay, these two values here, so that we can get this expression here by itself. All right, so I'm going to divide by that on both sides. Okay, so then of course those will cancel out there. All right, so then you'll need to divide those value numbers out there, okay, and then whatever that equals will equal TF minus 22.9. All right, so then whatever value, okay, you should put that there, solve for TF, and in the end, if you do it correctly, so you should check your math, your final temperature should turn out to be 27.7 degrees Celsius. Okay, so you should do the math on your own to make sure that you are able to get the correct answer. All right? Okay, one last thing that you need to know, or at least a couple last things you need to know for this chapter. One of them has to deal with Hess's Law. All right, so this is all review. The last part of this is all review from first year chemistry. So Hess's Law, all right, this is where we're going to manipulate the equations. So if we reverse an equation, we're going to reverse the sign on the delta H value. If we need to multiply the equation by a number, you do the same thing to the delta H value, okay? Then what you're going to do is you're going to add the equations up together, like this one only has 2, then you would add the equations up together, and then that would be your delta H value, all right? So they give you a desired equation. So this is the equation we're trying to solve the delta H for. It's right here, okay? So what they want us to do is they want us to manipulate these two equations so that in the end, when we add them up, it should match this. Okay, so what I usually do is I just take one thing at a time. So if I need 4 NH3s on the left-hand side, I look at both equations. Which one has NH3 in it? Look, this one does right here. And it's already on the left-hand side. But this one only has 2 of them, and I need 4. So what do I have to do to this equation to make it equal to 4? Well, I will need to multiply by 2. So then I'm going to multiply the bottom equation by 2. Since I multiply that bottom equation by 2, I do the same thing to that delta H value. Okay? So then that becomes 4 NH3s. When you multiply it through, it multiplies all the coefficients in the equation. Okay, so then 2 times 3 is 6 N2Os, and then that would be 8 N2s and 6 waters. Okay, then don't forget you need to multiply that part by 2. Okay, and then I keep looking. I need 3 oxygens. So I look in the equation here. It has oxygen right there, and there's no other equation that has oxygen in it. And I need 3 of them. So this equation, notice the oxygen is on the right-hand side of the arrow, and I need the oxygen on the left-hand side of the arrow. All right? So then that means I need to reverse the equation to get the oxygens on the other side. So I'm going to reverse this equation, which means I'm just going to rewrite it in the opposite direction. Not only am I going to reverse it to get it on the left side of the arrow, but look, I also need to multiply it by 3. Okay, so I need to reverse and multiply by 3. So this whole equation here is going to be reversed and multiplied by 3. So then it changes the sign over here. Since I reversed it, now it becomes a positive 164. Okay, because I had to reverse it, and I need to multiply that one by 3. Okay, so let's reverse it and multiply by 3. So then that becomes 3 O2s, right? 3 times O2. 3 times 2 right there is 6 N2s. Okay, you see how I'm reversing it? This was on the right-hand side. Now I flip those to be on the left-hand side. And now this is going to go on the opposite side. So this 2 times that 3 is 6. So 6 N2Os. All right? So then don't forget what you need to do over here. This needs to be multiplied by 3. This needs to be multiplied by 2. All right, now we're going to add these 2 equations up together. Whatever we have the same on the left and on the right, we can cross out. Whatever is on the same side, you're going to add. Okay, so let's take a look at one thing at a time here. You can see that we have 4 NH3s here, but we do not have any NH3s on the right-hand side of the arrow. Okay, so we have to keep that. All right, 6 N2Os. Oh, look right here, 6 N2Os. So those can cross out. Okay, let's keep looking. 3 oxygens. They cannot cross out. 6 N2s. And then right here is 8 N2s. So we can reduce those down. It's like subtraction. So that means we can get rid of all 6 of these. Therefore, we're going to be left with only 2. Okay, because 8 minus 6 is 2. All right, so then we have this that's left. That is left. 2 of the N2s. And then the 6 waters. So let's just rewrite that nicely. So 4 NH3. 3 oxygens. 2 N2s. And 6 waters. All right, now we're just going to double check just to make sure that this equation here matches what we were trying to calculate the delta H for. And you can see it does. There's the 4 NH3s, 3 O2s, 2 N2s, and 6 waters. Okay, now you just need to add those up there, right? Add those up right there. Okay, do the math when you add those, and in the end, you should get, and I wrote my answer in scientific notation, I got the delta H value to equal negative 1.532 times 10 to the third. And the units are kilojoules. All right, so that's what I got. Now, some of you are probably wondering, oh, I didn't get that answer. but remember this is in scientific notation. So if it's to the third power, that means you're going to move this decimal 3 places to the left. Okay, so that is how you do Hess's Law. Once again, that was review. So now the last thing that we need to review is the standard enthalpies of formation. Okay, so we call this the delta H, and there's a little F for formation. Okay, this is where we did the products minus reactants by looking at the delta H values. You will have a table. You actually do need a table, so the values will either be provided for you, and they are in your textbook though. Okay, they are in Appendix 4 of your textbook. So remember that elements in their standard states are going to equal 0. So if it's a diatomic, or if it's something that is not combined with anything different, okay, and it's all by itself, it's going to equal 0. So that is something that we learned last year. All right, so then let's take a look at this equation here. They want us to use the textbook, look up the Appendix 4, and we're going to find these values. All right? You have to be careful. You have to pay attention to the states of matter. Okay? If that's a gas, make sure you look up the value for a gas. And this is water in the liquid state. You have to use the value for water in the liquid state. Notice that there are some coefficients here. If there's a coefficient, you multiply the value in the chart by the coefficient. Okay, so don't forget it is products minus reactants. So I'm going to lift the page up a little here to give us more room. All right, so then I'm just actually going to write down the values for you since you probably don't have the table out right now. So just for speed reasons, let's see. So then the C3H6, if you look that up, you should always double check these values to make sure I looked up the correct value. In the gas state, I found that to be 20.9 kilojoules. Okay. The oxygen, the diatomic oxygen, all right, that is an element in its standard state, so that's going to be 0. The 6 CO2s, negative 393.5. Okay, all these units are going to be in kilojoules. And then water, but remember, it's water in the liquid state. Okay, water in the liquid state turns out to be negative 286 kilojoules. All right, so then to solve for the delta H, remember it's products minus reactants. Okay, if there is a coefficient, we multiply the coefficient by the value in the chart. All right, so the product side goes first, which is this side right here. So 6 times the value in the chart. So we're going to add everything that's on the product side together. So that's 6 of the waters, so 6 times that. All right, so those are the products. All right, those are the products. Now we're going to do the reactant side. So 2 times that value. Use a bracket. Let's group it. 2 times 20.9. And then 9 times 0. All right, we already know that's going to be 0, so I'm just going to put 0 there. All right, so finish out the math. Do your math very carefully. This side should end up being negative 4,077. And then this other side over here ends up being, so products minus reactants, 41.8. And then in the end, your delta H value should be negative 4,119 kilojoules. All right, make sure you double check my math to make sure I did it correctly. All right, and that is everything that you need to know for chapter 6. All right, and I will see you later. Bye.